This particular booklet is only about half of what it will be when we're done, because the printing shop is 5 days behind, so I had to already send out before, because I'm still working on it actually as we speak. So it's coming, so it'll just be around the corner. Thank you, Diane. See, it's like a well-oiled machine here. Okay, so I will leave this first page blank for now. My goal is to, once we've done a bunch of stuff, coming back to the front, and I will give you a map. Like, this is all the stuff we've done. It's going to be a visual representation. So I'm leaving it for now, because otherwise you're going to drop the course after today if I tell you everything we're doing, okay? But don't be scared. I'm just preparing you a little bit to not take it too easy, okay? So what is it, October 2022? I'm just writing that down for myself. So here we go. So let's go over to that first page there. 4.1. So principles of counting, or counting principles. So I kind of walk you through, and I will use my iPad from time to time to give you like a more vivid illustration of what's happening. Okay, so here we go. If one task can be performed A ways, right, A number of ways, and a second task can be performed B number of ways, then the two tasks together can be performed in A times B number of ways. So I'm going to highlight that part. This is basically what we're building on. That's our starting point. Okay. This is called the fundamental counting principle. All right, from now on, I'm just going to talk about it as FCP. Okay. This is only true for tasks that are related with the word and. Okay. And sometimes that word and is invisible. Okay. It's invisible, but it's implied. And what another thing I want you to think of is the A times B ways is a very small example. This can be applied to, if you have more things that are happening, you can go A times B times C times that, right? Like, as many events as there are, we keep multiplying it. So hold on for a bit, hold on for the ride. I'll explain this in a little bit when we do examples. Okay. If tasks are related with the word or, right? If you ever see the word or, okay, we use the principles of inclusion and exclusion, pi, in a sense, right? And we will most likely be using this formula, maybe not explicitly, but I will use this reasoning to address that, because there will be some overlap, as you will tell down the road. Let's apply what we've just learned, okay? So let's say you have you're flipping a coin and rolling a four-sided die. Okay, so flipping a coin would be event number 1, and rolling a four-sided die would be event number 2. Write that down, event 2, like that. How many outcomes are possible? Okay, what is the sample space? And we will show this using a tree diagram, an outcome table, and the FCP. What is that again? The fundamental counting principle. We're going to do this in 3 ways. Okay, so this is the first way here. Tree. And do you mind closing the door? Otherwise, it's gonna keep doing that. Thank you. Tree diagram. We'll do that first. So just so you know, I'm going to use about this much for the tree diagram. The middle is going to have the outcome table. Okay. So that's, or maybe a little bit more than half for the tree diagram. So here's a tree diagram. So let's say flipping the coin is your starting point. So you branch off like this. So what are my 2 choices when you're flipping a coin? Heads and tails. That's right. So two things that are happening first, and then the second event involves how many choices? 4 in this case. So we're going to go 1, 2, 3, 4, and then we're going to go 1, 2, 3, 4. I hope you can see that. Okay. So basically, what we'll do is we'll go 1, 2, 3, 4, 1, 2, 3, 4. Let me zoom into that a little bit. It seems a little small here. Okay, I can do that for now. Focus there. So what you do is when you do a tree diagram, you will follow the ends, the tips here. How many options are there? 4 and 4. You end up with 8 options. And here it is. Option number 1 would be to flip heads and get a 1, or flip heads and get a 2, or flip heads and get a 3. So this is actually stating your outcomes. The next one would be tails 1, tails 2, tails 3, tails 4. Okay? So I will put a line underneath here. There are 8 outcomes. How many of those outcomes involve heads? 4. And 4 tails, right? How many outcomes involve rolling or getting a 3? There's only 2 outcomes, right? This one and this one. Right? So I can ask in many ways. I can ask you for things, and this shows you exactly how many are there. There's a visual representation. Next, let's do. I don't want to do it the other way because it's going to take too much time and space. But could we have started with the 4? Like first do the die and then the head? We could have. Can I show you? I'll just show you on my draft here. So I could have started with rolling die, and then every single one would have 2 branches, heads, tails, because that's the second thing you're doing, flipping the coin. And you still get 8 outcomes, okay? So it doesn't matter which order you do them in, you get the same results, okay? Let's do the table. So this is the tree diagram. We're gonna do the outcome table. You will need to be comfortable with both, okay? Maybe as early as tomorrow. So what you do here is you basically just go, order doesn't matter. So heads and tails, right? Those are my options. So you make a table in a sense. Okay. Doesn't have to be pretty. But in that table you write down, right? 1 heads, 1 tails. 2 heads, 2 tails. 3 heads, 3 tails. And you get the picture. So that's your outcome table. Again, you could have done 1, 2, 3, 4 along the top, heads, tails along the bottom. It doesn't matter. You get the same results. So can I just say this? When I ask you to actually state the outcomes, like this is what I want you to do. Okay, write it out like this, or in an outcome table like that. Okay, and that's your sample space. So 8 outcomes, 8 possibilities, 8 ways to roll and flip a coin. Okay, then is the fundamental counting principle. Event 1 is the coin. I have 2, right? Event, this is what I'm going to use most of the time, the fundamental counting principle, sorry. I'm going to use this most of the time. Event 2 is the die. And in this case, it's only a 4-sided. So we go 2 ways times 4 ways of doing that second event. There are 8 outcomes. What's happening here? Oh, you can't see that, can you? There. 8 outcomes. So that's using the fundamental counting principle in a way, okay? So let's say you did 3 things. Flip a coin, roll the die, and pull a card from a deck of cards. 3 events. How many cards are there in a deck of cards? Did I give you that? 52? 52? So it would be 2, right, for flipping the coin, 4 for rolling the die, 52 for, right, you have 52 options from a deck of cards. So obviously the number of outcomes would be significantly bigger, right? You don't want to do a tree diagram for that one. That would be a good bonus question, wouldn't it? Anyways, no, we're not going to do that, okay? No nonsense in this course, okay? Then we go over to that second example. Suppose you're flipping 3 coins at the same time. How many outcomes are there? Use a tree diagram and confirm using the FCP. So tree diagram for 3 coins, heads and tails, right? And then each of them for that second event, heads, tails, heads, tails. And then the third event, you branch off again, happens to be 2 options, heads, tails, heads, tails, right? How many options would you have in this case? You count the ends, like the tip of the tree here, 1, 2, 3, 4, 5, 6, 7, 8. 8 outcomes. But if I ask you to list them, I want you to do this. You follow heads, 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 and the second outcome would be heads, heads, tails, and then it'll be heads, tails, heads, so you gotta be careful, and then it's heads, tail, tail, and then I go here, right? Tails, heads, heads, tail, heads, tail, and then here it's tail, tail, heads, and the last one is all tails. Those are your possible outcomes. So I'm just going to check 1, 2, 3, 4, 5, 6, 7, 8. I've got 8 outcomes written out like that. Okay, so just 8 outcomes as per the tree diagram. Can you do an outcome table with this one? With 3 events? You can't. Like when it's more than 3, I don't. I just go tree diagram if it's required. So fundamental counting principle, we would go coin, let's go coin number 1 times coin number 2 times coin number 3. So there are 2 options for each of them. And of course, we're expecting that 8 anyways, but here it is, okay? If you have multiple choice questions, do you have teachers that all they give you is multiple choice on a test? You have courses, maybe chemistry, or like there's a significant chunk, and you have 4 options on each question, right? So how many ways can you answer that test? Well, 4 for the first question, 4 for the second question, 4 for the third question, and so forth, right? So there are many ways of answering a multiple choice test, right? Because there's so many options and so many questions. All right. Let me see if I'm missing anything. I want to do this one just to get your brain going, because later on that's coming back. How many outcomes? Scan this. How many outcomes involve at least 2 tails? At least 2 tails. I'm gonna go. Oh, right there. 1, 2, 3. Can you count that one? At least 2, right? So that's 1, 2, 3, 4. How many outcomes with only heads? 1. Only tails? So that's what I'm going to start doing down the road, right? Like we're going to do probability using this. Okay. So anyways, let's keep on going. Steven plays soccer. His team has 3 jerseys, right? So that's important. I'm going to highlight that. That's kind of like your first option or first event. 2 pairs of shorts. How many different outfits or combinations are possible? Draw a tree diagram showing all the outcomes. This should be a slam dunk, guys. Like on a test, on an AC, get full marks on this one. Okay? So jerseys first. Red, white, black. That's fine like that. So this would be jersey if you want to put it down there. And then 2 pairs of shorts. So for every jersey, you technically can use both pairs of pants, right? So shorts are black and red, black and red, black and red. Okay, so now we write out the outcomes. That's also called the sample space. Have you heard of sample space? And remember, did I talk about it in statistics in grade 11? I'm not sure. RB, RR, red, red, right? White, black. white and red, black, black, and black, red. Okay? So there are your outcomes. With the FCP, we're going to confirm, right? We've got 3 options for jerseys, and we've got 2 options for shorts, so that's 6 outcomes. No surprises. We did expect 6 outcomes. You get that picture. Okay? If now, for example, we would add a jersey, a different color, or we would add socks, things would change. So let's go over to the next page. I'm actually doing that on the next page there. Backside here, B, if the team would add socks, right? I think it's supposed to be striped, not stripped. Sorry. Stripes and striped and solid. How many outcomes are there now? So you've got jerseys. You've got another event, which is your shorts. And you've got a third event now, which is your socks. And you're thinking, event? Why are you talking event, Mr. Erickson? I count them as events, right? So you've got 3 jersey colors, 2 shorts, and how many types of socks? You've got 2, right? So that's 4 times 3, which is 12 options. So you can say, let's do this. Sample space is 12, okay? It's the same as the number of options. Sample space is the same as how many options are there, how many combinations are there, okay? And so that's tree diagram, okay? Fundamental counting principle is what we're going to use 95% of the time when it comes to this stuff, okay? Next, let's talk locks, okay? A luggage lock has a 3-digit code with each digit is from 0 to 9. How many possible combinations are there if, so now we're going to do a bunch of scenarios. I need you to know this. If you're going from 0 to 9, how many options are there? Okay, there are 10 options. 1 to 9 would be 9, but if it's a 0, then there's 10 options. Okay, there are 10 options for each event. You're like, what do you mean event, Mr. Dirksen? What's event number 1? The first number on your lock combination. The second number, and the third. Because think about it, the only way this lock will open is if all 3 things happen at the same time, correct? This and this and this. If you get even 1 wrong, it's not a possible combination. So we're going to go times. So we're going to go 10 times 10 times 10. 10 to the power of 3, which is just 1, and then add 3 zeros. How many numbers are in your locks in your locker that dial? Up to 35? 50? I guess they're different. Like locks are a bit different. 60? Okay. So that would be for your locks, depending on your locker, right? And your lock would be 60 times 60 times 60, or 50, 35, whatever it is, right? So that's how, like, somebody guessing your code is, and then on top of that, they have to get it right, you know? Left, right, left, or is it right, left, right? I don't know. I don't want to mix you up, but anyways. Repetition is not allowed. This is key here. Repetition is not allowed. Okay? You can't use the same number more than once. Okay? Not allowed. Circle not. Okay? So we go back to the beginning, right? You look at that question. We have 3 digits. So for the first number, you have 10 options, right? How many are left now for the second? 9 and 8. You got it. You can't repeat, so your options are decreasing. Okay? So 9 times 8 is 72, times 10, 720 options. Okay? There we go. Only digits 1 to 8 can be used without repetition. If a question said that, this deserves your utmost attention. If it says no repetition, that's the first thing you should do. And then saying, hey, you can only use numbers 1 to 8. So we're still talking about a 3-digit block. So how many options do we have? 8 options, right? 8 options per slot, so to speak. Okay, so that would be 8 times 7 times 6. The no repetition, there's always one fewer item left. So here, anybody? So what I do is, this is 56 times 6, right? 336. And it makes sense, right? You're restricting, these are restrictions that are put upon you, right? So I'm making it more and more challenging, okay? First number cannot be 0. The first number cannot be 0. Repetition is allowed, okay? So we read it carefully and you can repeat. So let's go back to our code. So if the first number cannot be 0, you basically only have 1 to 9, right? That's all you have here. 0 cannot be it, okay? So you're like, wait a minute, Mr. Nixon, you just said 1 to 8 here. If it's an ABC, right, the 1 to 8 only applies to this question. When you get to D, you got to go back to the original, right, where you had 0 to 9. You can't have, so this is 9. And then how many options do you have for your second number? You're back to 10 because you can repeat, right? And back to 10 because all the other ones can repeat. So you have 0 to 9 here, 0 to 9 there. Okay, so what is that? 900, right? You would like the code to end in an even number. Okay, so you would like, it doesn't say anything about not repeating, right? So assume repetition is allowed. Okay, sorry about that there. So if it doesn't say anything about you can't repeat, then we're assuming you can do it. Okay, so even number, you would like it to end. So here you can only use 0, 2, 4, 6, 8. Those are your only options. That needs to be addressed first. So you have 1, 2, 3, 4, 5 numbers that you can pick. Okay, so we do that first, and then we deal with everything else. So here you can use 0 to 9, you can use 0 to 9, right? So 10 times 10 times only 5 options at the end. So what is that? 500 options, right? And here is where I introduced the OR. You see OR in capitals, right? So cases. Or, right, you have to split into cases. I want you to already start thinking about cases, okay? Case 1, right, starts with 3. So I'm going to go set up my code. So this is a 3 here. That's the only option I have for my first number. So I have one option for that one. Can I repeat? It says repetition allowed. Yes. So 10 times 10, because the other ones I have 0 to 9, 0 to 9 to pick from. So here I only have 100 options. That's if I were to start with a 3. Case 2, starts with 2. Okay, 2. I have 0 to 9 here, 0 to 9 there. So one option for my first number, and I have 10 and 10. So that's 100 options. So now you figured out that you have 100 codes that can start with a 3, 100 codes that can start with a 2. So how many in total? Total is 100 plus 100. That's 200 options. That would be your total there. And some of you are saying, like, Mr. Durson, couldn't I just have done 2 times 10 times 10? Yes, you could have done that. In this case, it would have worked. But I also want you to see that you can split it. Okay. How is this for a Thursday morning? Yeah, go ahead. All right, let's go back to the second page there. Or sorry, page 4. These are what's our timeline? Okay, we're doing okay. I want you to try these questions based on what I've just done. Okay, but I will set it up, and then you do the rest. Use pencil so you can erase if you make a mistake. But the Winnipeg postal codes consist of 3 letters and 3 numbers. Okay. The numbers use digits 0 to 9. The letters I to O, I and O are not used. Why would I and O not be used? I and O in a postal code. It's to not mix them up with numbers because O's look like zeros, so they just like, let's not do it. Okay. Find the number of postal codes if. So this is, I will start the first one for you. A postal code has 6 slots in total. And it's usually a letter, number, letter, and then it's number, letter, number. I would actually give this to you on a test, like I wouldn't make you guess, right? But that's the pattern that you observe, okay? I want you to try to look through all the way A to E and try to see what numbers would you have to fit in there based on the question right there. Do you know how many letters are in the alphabet? 26. Okay, just making sure. Okay, so you give that a try for a couple minutes. See what you would come up with, the numbers in here. I'm curious to see how you would set this up. So A to E, based on what we've just done, you can start now. Let's see how it went. Okay, a couple of observations that I'm going to make because this is about to change, okay? When we use digits 0 to 9 and letters, right, make a note that you have an unlimited supply. What does that mean, unlimited supply? Like, it doesn't say like there's only so many numbers in a bag or something. You have 0 to 9 to choose from. And you can take it as many times as you want. You can take the same one. So we have an unlimited supply of options, okay? So we've got 10 numbers, and we've got 26 minus 2, there's 24 letters, okay? So you've got 24 letters and 10 numbers, okay? So you need to know your options. So we go over here, and for everywhere, there are no further restrictions, which means that wherever there's a letter, we have 24 options, okay? Then I go to my number slots, okay? Wherever there's a number, I have 10 options to put in there. And so you got to make sure that you subtract the 2 for I and O, so you really have 24 letters in total. So here's where I want you to start being a little smarter with typing this in. So see that there's 3 10s there. So this is saying 10 cubed times, how many 24s are there? 24 cubed as well. So this is where it gets really big, right? The numbers get really big. So we know that you can go, this you know is 1,000, right? So I'm just going to go 24 to the power of 3. So you get that. And then I'm going to multiply it by, you can go either 10 to the power of 3 or just 1,000. So there's a lot of postal codes. So you've got 13 million, almost 14 million postal codes. Okay. That can be made. Okay. All right. What if there's no repetition allowed? So you do the same thing. Right? Letter, number, letter, number, letter, number. Okay. So you've got 24 to start. You can only use 23 for the next and 22 for that third slot. Okay. So no repetition allowed. Then for my number, you've got 10 to start with, 9, and 8. Okay. So there it goes a little different. So you type that in, and whichever, I will just move this up a bit. So you've got 240 times 23 times 9 times 22 times 8. So that is 8,743,680. So 8,743,680 and 680 codes, right? Codes or possibilities or options. Can you imagine making a tree diagram for this? Yeah, you wouldn't want that, right? So we started small, but then I showed you that the fundamental counting principle, right? We're using the fundamental counting principle for all of these, okay? Fundamental counting principle to come up with the number of options, because we understand that all of these 6 things have to happen for you to get a postal code. You can't have a postal code with 5, right? Try getting away with that. Amazon would not ship to your door. They would say, hey, you need to have 6, right? And it needs to follow that format. First letter must be an R. Repetition is allowed. So let's start this over again. So 1, 2, 3, 4, 5, 6. Make sure you write this down, okay? The first must be an R, and then we have number, letter, number, letter, number, okay? So obviously you only have one choice for the first slot. That's all you have. Repetition is allowed. So I actually have 10 options for my numbers and letters. I'm back to 24, correct? You agree with me or no? Not sure. Anyway, so we've got 24, 10 cubed, right? You've got 3 10s and 2 24s. Okay? So you go 24 squared, right? Times 1,000 or 10 cubed. So that's 576,000 codes can be made if that would be a restriction. So a lot of the postal codes in Winnipeg start with an R, correct? Almost all of them. So right, like for Winnipeg, it's for Manitoba, it's down to this many codes. The first letter may be an R or a V, RV. No repetition is allowed. Very important. That is very, very important to keep in mind. So what's happening first, Mr. Dirksen? Well, let's do R or V like this. I will do it in cases. And then we're going to do our second case. Okay. So we're going to do the case with an R and the case with a V. Did some of you just put a 2 in the front? Yeah. You're going to get the same answer, so don't erase. If you did everything else right, you're going to get the same answer. Okay, so trust me. So 1 there, and then we have, I got to get this right. No repetition allowed. So 10, 9, 8, correct? And then I have for letter 23, because I used R. I use the letter. I'm down to 23 and 22. So we're going to get that. And then here it's the same thing. I have one option there, 10, 9, 8. And for the letters, same thing, 23. You see how it's really the same? You see how it's copying, right? So if you did 2, like if you put a 2 here, then you're doing the same thing that I'm doing here. I'm splitting it into 2 cases. What is this number here? Let me see. I'm going to cheat a little bit and look at my key. 364, 320, correct? And this is going to be the same. And then I combine them, and I get 728, 640 codes. Okay? So if you looked at R or V, then it would be that many codes. Did you do all right by yourselves? If you didn't, you're not going to be like, of course, I don't get it, right? Don't worry, this is very fresh, right? This is new. I couldn't have prepared you for this in grade 11, okay? Repetition is allowed, but no vowels can be part of the... I just want you to know, how many are there? 5, right? There's 5 of them. So I started with 24. I need to subtract 5. There's 19 letters. Oh, yes. I did this on purpose. I should stick to my script. I know, so it's -3. Where?
Are we supposed to be taking out I or O? For I or the beginning of the sentence says take out letters I or O. Is it L or O or I or O? It's one letter. If it was I, wouldn't there be a dot on the top?
It's because all postal codes are capitalized, so
Yeah.
if it's a capital L, there would be a thing, so that's not a problem.
Yeah, it's I and O. But you caught me. You caught me. This is pretty good. I like that. I and O has already been taken away, right? So really, there's only 3 more that I need to take away. 24 minus 3 is 21. Remaining. Okay, there's only 21 remaining from my... Or you went 26 minus 5, you'd still get 21, right? So there we go. Repetition is allowed, but no vowels. So we have 21, 21, and 21. And here we have 10, 10, 10. And that, I want you to start doing this. It's coming back later. So 10 to the power of 3 and 21 to the power of 3. That's when you are allowed to repeat, and you're going to see the same number over and over, right? So you just use a power. So 21 to the power of 3 times 1,000. That's 926,1000 codes. There we go. 9,261,000. Okay. Try 6 on your own. Yeah. No repetition. You've already used one letter here. And you're down to 20. Oh, because this is R or V. So the 2 is kind of just, instead of doing the cases, you're doing it at one shot. But then you almost have to look at it as A to R. V. Of V, right? You'll still be down to 23. Which is let me just pause this, or else it'll be very... Let's see here. 6 multiple choice questions. That is saying 6 events. Right? And you've got 5 options per event. Okay? So what you would have to say is you would have to make 6 slots. Right, there are 6 questions. Question 1, question 2, question 3. Okay, and each one has 5 options. So this is 5 to the power of 6. Yeah. And what is that? This 15,625 ways to answer. Yeah, possible ways to answer, possible combinations. How many ways are there to get them all right?
1.
There's only one, right?
Yeah.
Unless your teacher made a mistake. So can I do probability real quick here? A probability of getting all questions right would be what? 1 in 15,000, right? 15,600. That's your chances of getting it all right. Let's get it as a percentage. Do you remember how to do that? 1 divided by 15,625 times 100. 0.0064% chance of guessing and getting them all right. This is random, right? Like it all depends on you randomly guessing. If you're making an educated guess, your chances get better, okay? If you can eliminate the obvious ones, your chances go up, right? There's an art to multiple choice answers. There's an art to it. Like if you can look at YouTube videos, they train you how to like eliminate the obvious ones, right? And then you do the rest. What's our time? Oh, we're still doing okay. Next, I think I want to do something because I see where this is going down the road. Okay, so I'm just gonna say that I'm gonna highlight the 5 with the 5 options here, and the 6. The 6 is your events or number of things that must happen, right? I don't know. I like to see like, okay, the 5 would be my options, and this. Okay, got it. Okay. This goes right back to the combo, the lock combination, right? 10 to the power of 3 because you have 10 options and 3 slots to fill in, right? Let's go here. B, how would your outcomes change if you eliminated 2 options for each question? Yeah, you know, the obvious ones. What is the difference? They want to know the difference in outcomes. So again, we've got our 6 questions. And now we have only how many options? 3, right? Because you're eliminating 2. So that's 3 to the power of 6. What's 3 to the power of 6? Anyone? 729. Look at my mental math skills. That was cheating. 729 outcomes now, right? Look at how many, like if you eliminate 2, right, there's a lot fewer ways to answer now. So difference would be 15,625 minus 729. So 14,896 fewer outcomes. Okay. Probability of all right would be 1 over 729. And 1 divided by 729 times 100, your chances are 0.14% more or less. Okay. So a lot better. Still not great, but better. So if you could eliminate 1 more, then your chances would be significantly increased. I want to, again, put a little break in here. I want you to try example 8. Skip 7 for now. I want you to do 8. Because I feel like if I'm just talking through these, you're falling asleep. There you go. Try and keep it. All right. MPI has license plates, obviously. How many combos are there? I'm allowed repetition, so I'm going to go 26 times 26 times 26, right? Letter, 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 followed by numbers. And so that is what? What numbers would you assume are allowed? 0 to 9, right? So 10 times 10 times 10. Okay? So it's 26 cubed times 10 cubed. Let me just check here. That's 1,757,6,000. Okay, 17 million. A bit more than postal codes, right? Plates. So write down the whatever context we're in, put that down. Okay, so plates. How many possible combinations and no repetition allowed? Allow me to just quickly do this. You don't have to do the line every time. Okay, you don't have to do those lines. I kind of just tend to do that for you to see. So what is that? 26 times 25. I have the answer, but I'm just gonna almost. So there's no repetition. That's what it would be. Don't put any decimals or commas. Okay, just leave it. Don't put commas in there. MPI customers allows customers to buy Jets plates, right? That start with a J or a double Winnipeg Jets, I guess. How many plates can be made if digits 0 to 9 can be used and repetition is allowed? So the OR is a big plus. Okay, so that means that for the first one, if it's J 1, 2, 3, 4, 5, and the other one is WJ. Sorry, I should have done it a little lower. There, WJ 1, 2, 3, 4, and those slots are filled in with numbers. You know the drill, right? What if Winnipeg grows so fast they need more license plates? What would they do? How could they make more license plates? Because there's only so many, right? There's only 17 million. Because people have multiple cars, right? What would they do to this? What could they do to have more license plates? Add a number, yeah, add a number or a letter, right? So when I ask questions like that, that's your answer. Add options, add another slot for another number. Ontario has that, right? Is it 3 letters, 4 numbers, or is it 4 letters, 3 numbers? I have to check. But they have one extra slot. Okay. Oh, sorry, I'm not done this, right? So this is basically J. Sort of. I just want you to see that. I put a J there. Technically, what I tend to do is I put J, so there's only one option for that first slot, so to speak. You understand that? That's really what's happening there. WJ, it's almost like the first one has to be W, the second one has to be J, right? So, but ones don't really make a difference in our calculation. So this would be 10 to the power of 5 plus 10 to the power of 4. And that is 110,000 plates. Right? And then now they're doing also like every group kind of has their own plate, right? The Humane Society, the Gold Eyes, the right, like every bombers, like there's so many plates that they're generating now, which kind of helps them, right? Okay, so let's go now. This is going to be pretty much one of the last things I'm going to talk about. I might do one example on the back side there. Let's do 17 because that's a different. This is a bit of a different scenario. If there are 5 racers competing, how many ways can first, second, and third place be arranged? Okay, and note, since we're talking people, obviously you can't have repeats, right? If someone is first place, you can't use that same person for second place, right? So I will put this down, limited supply of options. Okay, this is similar, listen carefully, when you have numbers in a bag or letters in a bag or something, as you're drawing, that the options are reduced, right? So that's almost saying no repetition allowed. It's the same thing. Okay, so you have to read carefully. So let's go like this: first, second, and third place, right? That's what we're wondering about. So those are our three events, and they all have to happen at the same time, right? So you've got 5 racers for the first place. Now, one of them has been attributed to first place. There's 4 left for the second place, and therefore 3 left for the third place. Okay, so this is 20 times 3, 60 options. Okay, there's 60 ways to give first, second, and third place. Obviously, skill level is not in the mix here, but this is potential ways of getting your final lineup of 3. Okay, limited. So how about we say no repetition? Therefore, no repetition. This is perhaps for me the most challenging unit to explain and to make students understand. Okay, this is the most challenging unit for me because I get it, but I got to make sure that you get it. And so this one is a challenging one, but I will come up with various ways of doing that. For homework, and you can already start, if you just go to the back side here, there I want you to do 6 and 7. 6 and 7. So I will put at the top here homework and homework, right? Pages 6 and 7. Page 6 to 7 in the notes. Okay, so, and if you want more, if you want textbook questions, at the bottom of page 6, do you see that? Bottom of page 6, there's actually textbook questions that you might want to try. Some will look similar to what we've done, others will look different. Okay, so I encourage you to dig in deep and figure out what do I need to do to understand this. Okay. I will say this, page 7 will be somewhat challenging, and I will go over page 7, but I need you to try it. I need you to at least give it a try. Have a number in there, and then we take it from there. Okay.